So first, we have Katie Carolan talking about Nebula's light, stellar nurseries revealed by the James Webb Space Telescope. Katie is an astronomer and helps run the nightly public observing program at the Griffith Observatory in Los Angeles. After receiving her degree in astronomy from USC in 2022, she started as an event business that focuses on delivering innovative and engaging astronomy, science, communication, and outreach experiences for the public. Today, in this talk, Katie explores the wonders of the Nebulæ, the cosmic nurseries where stars are born, through the revolutionary lens of the James Webb Space Telescope. Discover how JWST's advanced technology reveals the intricate detail and vibrant light of stellar formation, shedding new light on mysteries of our universe. Thank you, Katie.
Thank you, Robin. Thank you all so much for coming. I'm very jazzed about the James Webb Space Telescope, as I'm sure most of you are as well. We have some really beautiful images from Webb that we printed for this year, and I didn't even know which ones they were printing, but these two ended up in my talk. So for those slides, I will direct you to look at the really big version behind me. So my name is Katie, or you can call me Star Lady or Star Princess. And hi. And I'm an astronomer. I work at Griffith Observatory in LA doing public outreach for astronomy, and I'm the lead for Black Rock Observatory's observatory. And I love talking about space with people, and I'm really excited to talk to you today about baby stars. So first I'm going to talk about science and modern astronomy and the epic space telescopes that we have, and then I'll talk a little bit more about the way stars are made and how we see that star formation throughout our universe in other galaxies and our own. And then I'll talk about a specific interesting result that has come out of James Webb very recently, like 2 months ago. So first of all, I'm an astronomer, and as scientists, we're inspired by the same questions that inspire everybody. You know, where did we come from? Why is the world the way it is? You know, what's going to happen in the future? And astronomers and all scientists try to answer more specific versions of those questions that apply to their field. So in terms of star formation, we have how did the solar system form? Under what conditions do stars form? And what will future generations of stars look like? And how we address these questions is with really epic space telescopes nowadays. And this includes, for star formation, these 4 space telescopes. So Hubble, James Webb, and then 2 that are no longer operational but did some fundamental research in the last couple decades, which are Spitzer and Herschel. So giving them a shout out. And you'll see some of those images in the slides today. To look at the formation of baby stars, they are shrouded in dust deep inside star-forming nebula. So you need to figure out a clever way to see through these very, very dense, very dark nebula. And luckily, scientists figured it out, and you don't look with optical light, the light that we see, you look with light that is in the infrared part of the spectrum. So here's the full spectrum of light. Right next to the part that we see is the infrared portion. And this type of light just has an easier time getting through these clouds. When you look at the same region of the sky, this is the disk of our Milky Way galaxy. When you look at this in the sky, in all the different wavelengths of light, you see all these different features, and the image looks really different in each one because different parts of the universe glow with the different types of light. And so by looking at all the different types of light with tons of space telescopes, you get to see the full range of activity and cool stuff out there in the universe. But today we're specifically going to be talking about the infrared portion, which is what James Webb specializes in. All of its instruments are looking in different portions of the infrared part of the spectrum. And you can see more than star formation, but that's what I'm focusing on today. So we'll do a little compare-contrast between Hubble and James Webb. So Hubble had a really similar resolution, but it didn't have the same capability to see further into the infrared. So the clouds look darker. It looks more shrouded. It looks more more deep and dark and spooky. Whereas with the James Webb image, it's definitely a lot brighter because we are seeing more light coming from this area of the sky. And then compared to Spitzer, which is the direct predecessor to James Webb, so it had a similar range of light that it could see, but the resolution was not that great. And if you see how you want to zoom in on this interesting star forming region, you can see lots of detail here, and this is just such a blurry image. You cannot really look at individual stars as they're forming with this resolution. You just can't do science with that. So now we can. And this was an interesting region that we had looked at, with Hubble and right, so this is the same region of space, just a slightly different part of the picture. We looked at it with Hubble and thought it was interesting. We looked at it with Spitzer and thought it was interesting. So now we're looking at it with James Webb and discovering brand new things in the same region that we've observed with lots of different telescopes, which is just so exciting. So now, how do stars form? Let's do a little intro to star formation. Before you have a star, you have a protostar, and you can see in this illustration how there's a bright object at the middle and then a disk, an accretion disk around it. Not only do black holes have accretion disks, but also baby stars. They're pulling in matter. Gravity, the universal force of gravity is acting wonderfully in this case and pulling material in to form this baby star. You'll also see these jets coming out. That's just because not all of the material goes all the way perfectly to the middle, and as it's forming, it's also forming a new magnetic field with it, and that magnetic field can act against the gravitational pull in and shoot some of the material out, but most of it goes into the center and forms the star. And this happens over the course of hundreds of thousands of years. This takes a long time, but I think we can maybe understand that a little bit. Like, we as humans have a really long gestational period compared to all the other animals on this planet, and so stars, they do take a long time to form and be born as well. So now let's talk about how you might go from, can I take questions at the end? Okay, thank you, I appreciate you. So how do you get a baby star to start forming? Where do you get this gas? How does that go down? Well, let's start at the largest scales. You can see in galaxies this filamentary structure where the gas is starting to clump together, even on these really big scales. And in the brightest parts of this image, that's where the most active star formation is happening. And we can see it because it is brighter, because as these stars start to form, they're starting to heat up, and the ones that are in their last stages of formation are starting to spark on that thermonuclear fusion in the middle. And so luckily it is brighter in those regions. And when you look at all of these images, this is a bunch of galaxies that James Webb did a survey on, just to prove the point that all these different types of spiral galaxies all have this filamentary structure, and they're all forming stars in similar ways. We also see this when we look closer. So these images are from the Herschel Space Telescope. When you look closer in at those filaments, what do you see? You see more filaments, but you also get to start seeing those individual stars being born. These are areas, these cavernous areas are places where the star has fully turned on, and now that there's this giant crazy explosion going on in the middle, all this material is flying out, and it clears out the cloud around it and proclaims, "I am born," and reveals itself to us, which is lovely. But it also interrupts star formation, because any stars that were trying to accumulate more material, they just got blasted, and a lot of that extra material that was starting to clump together now has to restart. And so spiral galaxies are actually not that efficient at star formation, which is why they are still doing it 13 billion years after the universe started, after the Big Bang, because they're so inefficient, and every time one starts, it just blows all the other ones away, all the ones that are just starting to form. Then you end up having a really long cycle of having this over and over and over. In addition, we have other filaments that were found by Herschel, it basically did a survey of the entire galaxy and tried to see where all the filaments are and where's the star formation. Turns out there's filaments everywhere, and the less dense ones don't form stars, and the more dense ones have more material and they're more compact, and they do start to form stars. But it did find, it's one of its major discoveries was finding that there's just filaments everywhere throughout the galaxy. And there's something to be said about the filamentary structure of like our capillaries inside of us, and the filamentary structure of the largest scales of dark matter throughout the universe. So filaments, if you hear about them in astronomy, they're all over the place. This is just one place so that we see this structure. Here's another filament, and if you see this very overexposed bright region right here, you might want to know what it looks like. Well, the James Webb Space Telescope looked right at it, and it gave us this image. So this is the center of Rho Ophiuchi. This is an active star forming region. There's about 50 stars currently being formed in this area. There's this big cavernous bright white part. That is where that very bright star has turned on, and it is born, and it has blown away all the extra material. But you can see these two gigantic jets. Well, one is cut off on the top, so you can see the end of the jet a little bit better here. But there's a very obvious jet going like that. And that is where a baby star has not quite finished forming yet, but it is throwing out a lot of material along its axis of rotation. And that material is then slamming into the nebula around it, making it glow and making it look pretty epic. You can also see, I'm just going to point it out because I'm here, because everyone can see this one. If you can see right here, it's very dark in the middle where these giant jets come out either side, and you can see there's this kind of point shape here. This is exactly where this forming star is. You can't see the star at all. And it's surrounded by a protoplanetary disk, what will soon form a solar system around this star. And it's casting a shadow. So it's this disk around it casting a shadow. And so the light is able to come out the bottom and the top. And then we see this very distinct shadow around it, which we will see in other places throughout the presentation as well. We also have these wonderful nebula structure where you can see that it's definitely getting eroded. It doesn't look as clumpy as it could. There's lots of gas getting strewn about, and that's because you have these stars that are starting to actually turn on, and it's blowing away a lot of the material, but you can see the clumps. And those clumps are places where stars have started to form, and they've got enough material to hold on to it and stave off the erosion from these brand new stars that are being a little aggressive. This is the Tarantula Nebula. This is the most active star-forming region in our corner of the universe. In our local star cluster called the local group, there's about 80 galaxies in our local group. It is the official name, the local group, and which could be better in my opinion. But this region is the most active star-forming region. It's making the biggest, craziest, brightest stars, but even it has this filamentary structure. So we can see that these filaments, even in totally not normal situations where you're making crazy, crazy stars, you still have this filamentary structure around the outside. So the filaments are clearly important in the formation of stars. Here you can really clearly see this protoplanetary disk and then the light cones coming out from it. This one doesn't have as sharp jets, but you can see that there's totally material coming out and billowing out and fluttering out. So that will happen with any baby star. It's going to throw some material out, but sometimes it can be really aggressively straight, like a squirt gun coming out, and it will form what is called a Herbig-Haro object, which is basically where you see the bow shock of these jets just punching through the nebula around it and causing it to glow, and it causes different, and when the material from the star comes out and hits the material of the nebula, it transfers the energy, and so then it makes those nebula particles glow their own light. So it's not just lighting it up with the star's light, it's also giving it energy to glow on its own, which is very convenient because as astronomers, when something glows on its own, we can analyze the light and figure out exactly what it is. And so we get to see what all these clouds are made of. It's mostly hydrogen, but there's also these trace elements, heavier elements that have come from past stars that have died and exploded, and then that material comes together, being swept together by the gravity of our and the dynamics of our own Milky Way galaxy. And as it swirls around, it sweeps all the material together and forms these clouds. And we want to know what they're made of, and that'll also help us understand how these stars form, because different contents in different clouds will form different types of stars. It's all connected. Here you can see this image, which is another epic one, another Herbig-Haro object, where you can see that it's pretty obvious that like one side is a lot bigger and brighter than the other. But the jet, if you look at the very narrow jet coming out of both sides, it seems pretty much the same intensity. And that's because the reason why it looks like this is because there's a lot more nebula on the right side for that jet to slam into and make it glow. Whereas on the left, on the lower left, there wasn't as much nebula to punch and make glow. And the orientation is such that the big one is actually pointing away from us, and the little one is pointing towards us, just so you could try to make a little 3D image in your head of how epic this is. Now, let's learn about some new discoveries that James Webb has made. So obviously, I've been talking all about these filaments. They're very important, and we figure that the filaments will have a direct effect on how each of these stars form. And in our most simple models, we assume that the motion of the filament and the rotation of the filament and magnetic field of the filament will line up with the baby star as it starts to form, because where is that baby star coming from? It's coming from that material, and it's not going to have a random motion or a random magnetic field. It's going to start out with what it's got. And when you have that, you end up having the outflows of all of the stars, of all these baby stars, lined up with each other. Now, we had never seen it happen, though. We assume that that's what it was on the most basic level, but the universe is a pretty chaotic place. There's like 1 trillion stars in each galaxy, and there's a lot of dynamic things happening. And so we had never been able to see kind of like a pure, simple example where everything is lined up. But we were kind of just waiting for that to happen. And so James Webb, in June, finally discovered a wonderful, wonderful image where you can see all these outflows here, here, but here, this is a little bit easier. You can see the arrows are right next to the outflow, so you can still see the outflow is not on top. You can see this is going this way, this one. That's a good one. That's a good one. I like that one. And this, look at this fat one right there. It's so cool. So we were able to finally see a very young filament that hasn't been messed with too much. And all of these stars that are forming are the absolute youngest of the baby stars. They're like class 0. They're just starting out. So they haven't had time to wobble around. You know, if you spin a top, it won't be perfectly straight. It'll kind of do this. Well, the Earth also does that. So we have a tilt of 24 degrees, right? But our axis also twirls around. Similarly, as these stars continue on their formation, their axis of rotation will also start to twirl around. So we see that stars that are further along in their progression of formation, they're definitely all totally wonky to each other, and they're not even lined up with each other. So not only are these all lined up with each other, they're totally aligned with the filament that they are all forming on. And so this is James Webb data. It was also compared to SOFIA data. If you've ever seen a picture of an airplane with a big telescope in the side of it with a big door open, that was SOFIA. And that was able to give us this image just archival data. We had half an image, so we'll use it. And I've made the magnetic field lines in green, and I'll go back and forth so you can see that they're totally lined up with the axis of rotation as well. So this is the magnetic field of the filament, and then this is the axis of rotation of the star. And they're totally lined up, which is just nice so scientists are down for whatever result. If it goes against what you were thinking, then you have totally brand new science and you get to really ask a lot more questions. But sometimes you're happy with having your theories actually be right when you are able to observe. So we're stoked. We're stoked that the basic star formation principles that we were assuming were correct are correct. But one more thing, is that what the scientists are really doing? Are they just going like compare contrast on the two different images and saying that's science? Not really. This is from the paper that was released with these results, and there's lots of pretty images of all the outflows, but there's also this big chart of data that they extracted from it. Data, and then these graphs. Look at these graphs. Yeah, that's the science. That's the science. And then the conclusion is just this big wall of text. But I get to talk all about that and look at all these pretty pictures, and we all get to enjoy these pretty pictures, which is so wonderful. So thanks for learning about baby stars with me. I hope you understand how our universe actually forms and evolves a little bit more. If you have any questions, I would be very happy to take your questions.
Thank you, Katie. That was amazing. Very beautiful pictures. Yeah, like she said, happy to take any questions. I can walk around with a mic and hand it off to you. So could she?
Yeah.
Any questions? Raise your hand.
You had one earlier. Do you want to ask it? Do you remember it? Okay.
Protostar, the pictures of the protostar. I was just baffled that that's actually the picture. This is the picture of the.
Yeah. They're all super epic. They're all. I agree. Yeah. Any other questions? Yeah, right there.
What can you tell us about the colors in the photos just that we're seeing?
So the colors, so all of these pictures are false color technically and on purpose, but also these are all infrared images which are invisible to our eye anyway. So to turn that sensor image into a picture for us, it just starts out as like black and white data that's mapped to different wavelengths, and then we make it into a pretty picture. There's certain in each. There are some conventions for certain colors to mean certain things, but in general, you'll see that the brighter areas are usually hotter and the darker areas are cooler, especially when you're looking at gas clouds. You'll sometimes have different colors showing you where the different types of gases are. So like if there's oxygen, different types of oxygen could have different colors, like different molecules. There is only one type of oxygen, sorry. There are different ways to combine it into different molecules, and you'll have that be different colors. But in a lot of these, the colors often are showing you where the hot gas is versus where the cool gas is, because the hot gas is going to have a harder time clumping together to form stars. So we want to know where those more diffuse, hotter regions are, and then we want to see where the colder regions are, because that's where the gas is going to condense further. But also, just a shout out to the Space Telescope Science Institute. It's part of NASA, and there is a whole team of people who take all of the black and white science data and turn it into all of these insane pictures. It is not, unfortunately, it is not the scientists who are really the ones making these epic pictures that you see here. This is a team of people who are all professional science communicators who want to contribute to your understanding, but also make really beautiful epic photos for all of us to go, wow. And they don't change any, they don't embellish anything, they just make certain colors. Another question? Thank you.
Yeah, I was just wondering, so like if a star, once it's formed and turns on, it pushes everything else away. How do we get stars that are like super orders of magnitude different sizes? Like they all turn on roughly the same size?
So thank you for your question, that's a great one. the whole situation that filament and that cloud is in will contribute to how quickly the star will collapse in and turn on. So if you have also the how dirty the cloud of gas is, the dirtier it is, the quicker it'll collapse, which means you'll have less material there to form the star and before it turns on. So in the early universe, the clouds were very clean. There was no dirt. It was all hydrogen and helium, and that let the process go on for longer, and so you'd have this very long time for the material to slowly accumulate before the star turned on, which let you accumulate more. Whereas now, we've had many generations of stars live and die, and when they die, all of their the dirty, extra heavy elements that they create gets thrown out and put into the new stars, and that causes more turbulence in the cloud and causes it to collapse faster before it's had a chance to accumulate more material. So it has to do with the filaments and how dirty the clouds are, and also kind of the era of the universe that we're in. But we still aren't super sure how the ultra massive stars are formed. That is still an area of active study for sure. Same with supermassive black holes.
Yeah, I just wanted to chip in also that supermassive black holes, nobody knows how they form. That's a big open question in astronomy, is we don't have any good examples to be able to just look at and see that's how the supermassive black hole grows. But they're at the center of our galaxy and probably every galaxy.
And similarly, the really, really big stars, as they're forming, they are very shrouded. At the very core, they are very shrouded in dust. We can see lots of things around them, like in all these pictures, but we have never been able to see in great detail through those dense clouds into that disk. And that's why that first image I showed was an animation, was a drawing, because we don't have a picture of that.
Thank you, Katie. Can you tell us, or do you know, what the temperature gradient is of those colors, if those colors, say in the right-hand panel, are graded on temperature? Are they in centigrade or Kelvin?
I actually think... I can't remember exactly what the blue one is, because it was a separate thing, but I do know that the pink is molecular hydrogen, which is a lower energy hydrogen. But you can see the brightness definitely correlates to how hot it is, and that is just how much energy did it gain from that jet and that shock that's going out. But I have, if you come find me after, I have the whole description of this image on my computer, and you can read that, and it will tell you, it's like 4 paragraphs. Yeah. Did you have a question?
This star topography, the topography of the stars, what makes our universe, our atmosphere unique? Is the study of the stars helping people direct where we might find life on other, is a cluster all these babies going off? Is there enough room for an Earth potentially to be around?
So that's a great question. So once the star has turned on, it will often figure out a way over time to wander away from the cluster. And once it's out there, then that protoplanetary disk of material that was already around it has a chance to form planets. And so the planets, they start forming in this sort of area, but in general, it takes the planets a lot longer to form, and it's in a relatively more chill area of the galaxy. But then also, by studying star formation, we understand stars better. And when we understand stars better, we understand how stars behave and what sort of stars could support life. For example, the most abundant star in the universe are these red dwarf stars. And they're cool and they're small, and you might assume that they're chill, but they are not chill. they have these crazy explosive fits where they send out so much high energy radiation that it just would fry the surface of any planet, even far out in its solar system. It would fry any planet. So that's the most plentiful type of star. And you know, the only life we're aware of in the universe is here. And yes, it is in our oceans, but it's not like life here is only underground, right? So we know that life likes to flourish on the surface of a planet, and if the life around, if there was life that was just starting around this type of star, it would just totally get annihilated. So the fact that the most common star in the universe is totally not conducive to life on the surface makes me feel really grateful that we're on this planet around our star that is not that type of star and does not explode all crazy like that. And by understanding how stars form, we just understand more about their life cycle and the universe and stuff like that. Yeah.
Amazing. Thank you so much, Katie. I think we have to wrap up questions for now. I'm sure that Katie would be happy to answer any questions afterwards.
Thank you all so much.
Yeah, that was beautiful. Wonderful talk. Beautiful photos. And yeah, great to showcase some of the stuff that James Webb is already doing. Moving on.